So to continue now um, on this idea of comparing groups and performing these sort of tests. So we did the ICC before, and that's really for showing that the variability that we have is minimal and seeing that the metric we have is kind of reproducible. So that was the focus for that. But for performing tests and showing that two groups were actually different, it wasn't really the right approach, or it would be a difficult approach to use in many circumstances. And so once we know that the analysis that we're performing is reproducible, it's possible to start comparing groups. And so really the ICC is the first step to kind of validate that the whole measurement analysis process is giving somewhat meaningful results, that the variation within the measurements is low enough and the difference between the measurements is high enough, that we can actually now start to perform tests to show that the groups that we're looking at are different. And so in order to perform these tests, the first thing you do is kind of list the assumptions that you have about your groups and what you're trying to test in these groups. And the second aspect is to establish a null hypothesis. And so who can say what a null hypothesis is? People have taken stochastic calculus, but they don't feel comfortable saying what a null hypothesis is. No ideas.
The possibility, the hypothesis that what you're observing is due to completely random, or vice versa. Essentially, what you're trying to do in a null hypothesis test is to establish if anything you're observing is due to completely random, the probability that what you're observing is due to completely random events that would happen anyway. So, another way to say that.
Yeah. So I mean, it's the right idea. So typically when you're looking at comparing groups, the null hypothesis is that the groups are completely the same. And that the differences that you're seeing are due to random variation between the samples. And so the null hypothesis is that the groups are the same, that there's no difference. And so you sort of assume there's no difference until you've shown otherwise. And so what we do with this test and this whole idea of testing is you take the null hypothesis, so you start off assuming that they're the same, and you show that that's unlikely to be true. You don't actually prove that they're different. You don't show that they're different. You assume that they're the same, and you show it's unlikely that they're the same. And that's, I mean, it's of course not the only tool, but it's the most commonly used tool for showing this. And so you can see it's much less convincing when you actually look at how it's made than how people try to present it in papers. That usually people, when they present results in scientific work, they say, you know, we've disproved the null hypothesis, and this shows that there's a difference between group A and group B. And that's completely wrong. What they've shown is that it's unlikely that group A and group B are the same, and you can sort of take with that information and do what you want. But it does not show that they're in fact different. It just shows that given the assumptions that they've made and this null hypothesis that they're exactly the same, that that's unlikely to be true. But it could be that their measurements are terrible. It could be that their analysis technique was not well chosen. They could have too few samples. There's all sorts of possible explanations for why it's unlikely the null hypothesis is true. But what they in fact show is that it's unlikely. They don't show that it's 100% certain that the null hypothesis is wrong. And they don't show for sure that there's a difference between the groups. And so, yeah, usually when you're looking at this, the null hypothesis is sort of what's the probability that you observe the results that you have if the groups were in fact the same. And so you want this probability then to be as low as possible if you're trying to show that there's a difference between the groups. And so what it requires is it requires a very detailed knowledge of the probability distribution of the data, which means that you either have a very good theoretical model for how your system's done, or you collect enough data points that you can actually recreate this distribution fairly accurately. But this modeling can be sort of very complicated, and depending on your data, very difficult. And so this is one of the, or these two bottom problems, are one of the major issues you have with this kind of testing in general, is that if you look in tools like MATLAB or Python or even Excel, they have a t-test function that will compare groups. Inside of this function are hundreds of these assumptions about how your distributions are, about the statistical variation in the groups, about how everything is modeled, that it just applies to your data. But if your data aren't, or you can't apply these rules to it, then the result it gives you is completely meaningless. And so you have to be very careful that when you're using sort of these prepackaged tools, that they fit in with your model and your understanding of your distributions. Otherwise, you'll get, if you have garbage into the analysis, you'll have garbage out. And by making it too easy to perform these sort of tests, you hide a lot of the important understanding that goes into it. That these models that you use in Excel, for example, it just assumes you have a Gaussian distribution and that it can calculate the mean and the standard deviation, and then it moves forward. If you have anything but a Gaussian distribution, this won't give you the right answer. And particularly if you have distributions with sort of these fatter tails, where you have much higher likelihoods of rarer events than Gaussian, this can cause substantial problems with the further analysis that you do. But of course, to know that you have fatter tails, you need to measure a lot of the data so that you can see how unlikely very rare events are, or events that are very far away from the mean are. So if we go back to kind of the loaded coin example, that you sort of have one coin from a magic shop, you can list off the assumptions you have, and it's sort of you flip and observe flips of coins accurately and independently. So this is almost always one of the assumptions you're required to have, so that when you do these tests, there's no relationship between the first measurement and the second measurement. And so if you're looking at the same animal over time, then of course a t-test isn't the right test to use, because you assume that there's completely independent. And of course, if you're measuring how heavy an animal is every day, this isn't an independent measurement. It's quite dependent on what it weighed yesterday. The second is sort of the coin is invariant and always has the same expected value. So it means that there's no sort of temperature or gravity or some other component that's coming into it that could cause this expected value to change. And so as soon as you have a system where this isn't sort of always the same and all of your measurements are identical, then you don't have this assumption anymore. So for this, the null hypothesis is sort of that the coin is unbiased. So you'd have this expected value of 0.5, because that's what you've observed all in your life up until now, is that if you have a coin, it's 50% likely to be heads, 50% likely to be tails if you simply flip it. And so what you can calculate from this is we can calculate the likelihood of a given observation, given the number of flips. And so what we have here on the x-axis is the number of flips, and on the right axis, the probability of getting all heads if you have a completely fair coin as you go on. So if you have one flip, the probability of having one heads is 50%. That's pretty clear. It's when you go to 5 and 10 that this value starts to get very, very small. And so if you have 5 flips, it's then 3% probability that you have one head. And 10 flips is when you have then 0.1% probability. And the question that you have then here is sort of how good is good enough? How many of these flips do you have to do to be confident that your null hypothesis is in fact wrong, or that it's unlikely to be true? And of course, that depends a lot on what your data are and what your requirements for further analysis are. Cool. So, since we usually don't have all of the information required to create a distribution, there's a lot of sort of assumptions we can take to make it simpler. And so this is where the student t-test and student t-distribution come in. And that's that you assume the distribution of sort of the stochastic variable is normal, which means it sort of has a Gaussian distribution. And then the t-distribution provides an estimate for the mean of the underlying distribution based on a few observations. And so what the t-distribution is your data doesn't have the t-distribution. The t-distribution is the probability of what the mean value of this will be based on the observations that you feed in from your Gaussian distributed variable. And so you can use this to then estimate the likelihood observed values, assuming they're coming from a random observations of a normal process. So it's a process that you don't necessarily know what it is, but you can use this t-distribution if you know that your underlying distribution is Gaussian to kind of understand the properties of it better. And so I think this is a point that a lot of people typically stumble upon, is that when you have 20 measurements, that's all you have. You can calculate a mean for these 20 measurements, but that's not necessarily the mean for the system that you're looking at. That's simply the mean of the 20 measurements that you have. And so what's essential to be able to do for these further analyses is to be able to say, how do these 20 measurements that you have describe your original system? And so that's where this t-distribution comes in, because it gives you that link between the observational data you have and how your underlying distribution looks. So it can't be completely open. You have to assume that it's Gaussian for the t-distribution to be valid, but it will sort of tell you what the mean and what the standard deviation of this is based on the observational data you have. And that if you, what? Why it's called student, I have no idea.
No.
You know?
I looked it up once. It's a name. It's a pseudonym. It's actually a fake name given by the designer in early 1900s, who happened to be a Scotsman working in Ireland, and needed to maintain secrecy, so he gave it a quote himself, Mr. Student, when he published his real name. You have to look up other number. He was working for an Irish company and didn't want him to be published. Anyway.
Yeah. Good. Yeah. So the name doesn't have any mathematical background.
He was working for an Irish beer company, which is famous.
Yeah. Okay. But yeah, so that you have this, and that, I mean, that's sort of the important link to remember, is that these observations that you have really are just your attempt to measure your data. They don't actually describe the underlying process at all. And so there's a substantial disconnect between those things, and the t-distribution is what brings them together. And once you don't have a normal or Gaussian distribution underneath, then you can't use the student t-test or any of those tools anymore. In many cases, you can transform your underlying distribution to a Gaussian, or you can measure something out of your system that's Gaussian in characteristic, or if you combine enough things together, eventually you'll get to a Gaussian distribution. But this only works for when that variable is Gaussian. So when you have things that are very stochastic or have huge amounts of variation or uniform distributions, then you can't use a student t-test at all to compare them. But, so now looking at sort of this test that we come up with is that you sort of incorporate the distribution that you have, so this t-distribution, that it gives you a very easy method for assessing the likelihood that two sets of observations are coming from the same underlying process. And so that process can be the same sample or the same type of sample, but it can also be something like if you have two different temperature ranges you're getting out of your system, that the same type of heat is causing that, or whatever that might be. And so there you have to assume, again, the unbiased observations and assuming the normal distribution. And so now, if you go back to kind of this magic coin example, if you're trying to publish a paper, the sort of cutoff p-value, and this will change soon, hopefully, but right now p is less than 0.05. And so that means that there's a 5%, or there's less than a 5% chance, given the assumptions that you have, that the data came from the same underlying process. And so if we look at the number of flips that you take. If you have, 1, it's 50, 4 is 6.2, 5 is 3.1. And so that means that 4.5 or 5 flips, you have enough results that you could publish a paper. Which, if you think about it, it's quite scary, because to get 4 heads in a row isn't that difficult. I mean, if you try to do it right now, probably only one of you, or maybe 2 of you, would end up getting it. But there's probably none of you that have a magic coin in your pocket. So the 2 of you would have convincing enough results to publish a scientific paper from 5 coin flips is kind of scary. And so now, if you sort of look at this, what makes this even worse is that this is just if you have one person who's flipping coins. When you start to have more people that are flipping coins, if you have one person, the probability that they flipped 5 heads is 3.1. But as soon as you have 10, 20, 40, 80 people, the probability that one of them flips 5 heads gets very, very high. And so if you think a lot about sort of the very popular research topics, like cancer research and those sort of areas, there are easily 80 groups around the world doing research or flipping coins. And the likelihood that one of them gets a statistically significant result, even though the underlying system is completely unbiased, is 92%. And of course, as this number gets higher and higher, that becomes almost certain. And so this cutoff is actually quite dangerous, because it means that looking at noisy processes, you will eventually find results that seem significant. And that this 0.05 cutoff is in fact very low. You could actually require much, much stricter values, so much smaller p-value, if you wanted to be confident that every group is in fact finding meaningful results. Cool.
So what else could you do? So why is it that, 5% seems to me is quite usual.
Yeah.
So that won't be changed too soon. So what should a group do in order to make sure that the results are reliable?
So you can have much higher standards inside of your group. So you can say that you want to cut off at 1% or less. And one of the most important things that you do is that you really understand what this 5% actually means. And so that's kind of what this question, the number of friends flipping, that if you have 5 PhD students that are just testing hypotheses all day long, then someone is going to find a hypothesis that's true, even though the data is completely meaningless. And so one of the things that can be very helpful, which is actually one of the things I had to do during my PhD, was show that someone who was trying to publish a paper, their analysis and their approach for finding statistically significant results would find statistically significant results in noise. So I replaced their data set with a random number generator, and they got even better results than when they put their data in. And so this is a fairly convincing argument that in fact you didn't find this interesting link in your samples. What you found was simply noise. And if you look at the medical community, what they require is when you do a study, you're required to say before you do the experiment, this is the hypothesis we want to test. These are the number of samples we want to use to test it on. This is how we're going to conduct our experiment. You then do your experiment, and at the end, you do all the data in your analysis, and you have one hypothesis or 2 hypotheses that you test, and they're either true or false. If you look at the way a lot of scientific groups work, you do all of your experiments first. You might have had a hypothesis at the beginning. Usually you can't prove this hypothesis because you don't have enough data or your data aren't strong enough. And so you find another hypothesis that you can prove. And you search around until you find one. And basically, if you have this approach to science, you will always find a hypothesis you can prove. So if you take noisy random data and you test it enough, you will find a hypothesis that you can prove. Because these groups don't calculate the p-value correctly. So what this p-value assumes, in this case, is that, for example, here you have the number of friends flipping, that when you have this p-value is less than 0.05, this assumes one person flips one coin exactly 5 times. When you have 80 people flipping coins, then the p-value is no longer 5 flips, or the p-value is no longer 3% at 5 flips. You have to recalculate what the p-value would be so that you know that your result is significant. And so when you do this, you sort of have to take into account the entire situation. And that's not always done. Because how it looks for one person doing one experiment is different than 80 people doing the same experiment.
So
Yeah.
this is like machine learning, this would be like overfitting if your BC dimension is too high.
Yeah. Yeah. So his question was sort of for like machine learning. This is then the same problem as overfitting. So that when you have a machine learning setup, and that's actually one of the later slides, hopefully we have time to get over it, is that if you have too many parameters in your system, you can perfectly fit your data, but you actually haven't understood your data at all. You simply found a model that has learned all of your data points. So I think we can just got a lot to cover. So this was this idea of overfitting, that when you sort of have a tool to do analysis, and so here we sort of have a magic classifier, and you train it. And so this maps dog, so this maps some kind of animal, or let's say to a category. So it maps a thing to a category. And so here you have dog, it's animal, Bob is a person, fish is an animal. And so it kind of maps these things to categories, and this is the training that you perform. You can then test it on the training data again, and you sort of ask the magic classifier, what's dog? And it says animal. You ask it, what's Bob? And it says person. You ask it, what's fish? And it says animal. But of course, you haven't created any sort of magic classifier. You simply, this is a dictionary in Python, a hash map in Java, or C, or whatever other language you use. And that here, when you try to then ask this classifier, what's an octopus, you get an exception. It doesn't know what an octopus is because you haven't specifically trained it, and you haven't created an algorithm that actually learns. You simply memorized the inputs that you gave it. And so you see this as well if you do curve fitting. You can fit a curve that passes through every single point in your data, but has no predictive power. And so with machine learning, it's very important that you sort of balance these things out with how much predictive power does your model eventually have. And so the link isn't quite completely sort of 100%, but the idea is that if you find a significant finding, so if your p-value is very low, then if you were to do more experiments, you would continue seeing the same difference that you see now. And that's really what the p-value is telling. And in machine learning, the idea is that when you then give it new data, that it's able to accurately predict what the new data is. But in science, or sort of experimental science, you call this p-value. And you want a low p-value because it means that you've understood your data well, but you haven't overfitted it. And in machine learning, you call this overfitting because you don't want to simply memorize the results that you have. So basically what this moves on to is sort of the more general case of this. And this is what you see in many science groups is that you flip a coin until you get 5 heads. And then you say, yeah, because I calculated at the beginning that 5 heads in a row is sort of a 3.1% chance that that will happen, and so that's a significant result. And so I simply start flipping a coin and flip it until I have 5 heads in a row. And once I have 5 heads in a row, I can stop because that's statistically significant. And this, I think, you can quite easily understand with a coin why it's complete nonsense. But inside the scientific environment, it's much more difficult to see because you have much more complicated experiments and much different hypotheses that you're testing. And so that's why the coin model, I think, is very helpful, because you have sort of a much better intuition on what a coin should be. You typically don't have very good intuition on what the trabecular density in a mouse bone should be and what a difference there actually means. And so what you see with this is that, kind of you can take these simple scenarios and apply them to how you've done your research process, and if that would give you a significant result with random noise in or with a random coin in, then it's probably not a meaningful analysis that you've done, or you wouldn't be very confident in the results. And so this is typically what you have, is that you have sort of a setup where you keep tests, you sort of come up at the beginning with a bunch of hypotheses that you have, and then none of them are true, and then you just make up new ones until you find one that fits your data well. And that basically, with all of these statistical testing approaches, you have to have kind of a memory of all of the things you've tested on this data before. And so if you've already tested 5 hypotheses, then your requirement for proving your 6th hypothesis or being confident in your 6th one is much higher than if you hadn't tested the other 5 before. So that's a bit counterintuitive, because it seems like that shouldn't be linked, but it in fact is. And so this is sort of called the multiple testing bias. And so particularly for a lot of the metrics we've covered now, this is very dangerous because you can very easily get thousands of metrics out of a single data set. So you can take a data set and analyze it and spit out, the cell oblateness, the distribution oblateness, the distribution tensor. You can take all 9 terms from it and use it in your further analysis, but it gives you a ton of parameters. And the problem you have is that the more parameters you have, the more likely you are to find something that looks like it's significant that isn't. And so, kind of the dream of this would be you come up with all these parameters for your analysis and you throw it into some magical statistical algorithm and then push the publish button and get an answer out. But the problem is the number of variables you study. So if we take this old definition we had of significant of p is less than 0.05, and you increase the number of variables you have. And so this is just taking random variables and adding them to your system. That the likelihood or the number of significant findings you have, or average number, sort of steadily increases as the number of variables in your study goes up. So if you have 60 different variables, the likelihood that you have the sort of average number of results you have that are significant are 3. And of course, what this means is that your definition for significant is wrong, because you would not expect 3 significant findings in 60 random variables. I mean, you don't want to have any significant findings. And so what you do here is you do this multiple testing correction so that you correct for the fact that you're performing multiple tests. So you're not just looking at one variable, you're looking at multiple variables. And the more variables you look at, the stronger this correction factor becomes. And so in this case, it's simply dividing by the number of different variables you're looking at. And so you see it sort of turns this constantly increasing one into sort of a flat line that we have here. Can anyone think of what the downside of this is? So we do this approach so that we don't find significant variables that aren't significant. Why might this be a problem?
Maybe there is a significant variable, but you don't see that it is.
Yes, that's exactly it. So because you apply this correction factor, the barrier you have to finding a significant variable, or the hurdle you have, becomes much higher. So that, with the coin flips, we had to find 5 heads before in order to call it significant. And if we have 60 different people flipping coins, that you now need to find 15 heads in order for it to be significant. And so by choosing to look at so many different variables, you make your sensitivity kind of for each variable much lower. And so when you're doing these analyses, you have to be very confident that the variables you're looking at are interesting. And you have to decide that before you start doing any statistical analyses. Because if you don't, what happens is you can end up missing out on a lot of interesting parts of your data because the cutoff you set is so high that you're forced to ignore them. So basically, if you look at 60 different parameters in your data, your cutoff is 3 times higher than it would be if you just looked at 20. Or just looked at, or 60 times higher than it would be if you just looked at 1. So basically, you have this correction factor that forces you to ignore significant results because you're looking at so many different variables. And so it's important that you choose these variables carefully before you do the statistical analyses, because you have to take into account the total number of variables you're looking at before you start doing the analysis. And you can see that, again, quite clearly with sort of the coin flipping example, that if I say everyone in the class start flipping a coin, and I want to find if there's a particularly biased coin, then I can't say if someone flips 5 heads that that's significant. Because the experiment I'm performing is having everyone in the class flip 5 coins, and the likelihood that someone will have 5 heads with a normal coin is very high. But if I just have one person, and I say they can flip 5 heads, then I can stay by this. But what people do is they often do this whole 60 thing. So you have everyone in the class flip coins, and then you find the person who flipped 5 heads, so you find the variable that was significant, and then you say the study you did was just to have this person flip a coin 5 times, and this is significant. But that you're sort of going backwards and forwards along this path, and you're not allowed to do that. So that in this sense, each variable you have is a person sitting in the class. And if you're choosing to look at the entire class, then the requirement for a significant result isn't 5 heads. It's 15 or 12 or whatever heads in a row that you need to find. But if you just have one person, the requirement's just 5 heads. But you can't look at all of them and say flip it, and then I'll find the person who has 5 heads and go back to them and say that's a significant result. Because they're not the same thing. It's not transitive. Is that clear? Yeah?
But in this case, we cannot, because each variable is equally important in this case. So we have to set a higher threshold, right? So we will have to, if 60 people are doing it, we will have to say the result will be significant only if one person gets 15 hits.
Right.
We cannot decrease that. We cannot. So what you said here is that we have to be careful that the features are important.
Yeah.
So that the threshold is not too high.
Right.
We can't do that in the coin example because each feature is equally important.
Right. In the coin example, each feature is equally important. You don't know who's going to throw it in advance. But in the studies example, I mean, you sort of see the link is a little thin at this point. But in the study example, the 60 variables that you have, if you have 60, then there's no chance that you're going to find a very small significance. Because you're forced to throw that away in order to keep your analysis rigorous. But if you have a large number but if you can sort of decide, actually a lot of these variables aren't interesting, or a lot of them are very closely related. So instead of measuring these 5 different variables, I can just measure this one, and it gives me the same information. Then you can reduce this 60 a lot. The problem is you can't reduce this 60 after you've started testing. Because then you allow yourself to just pick out the results that you like, that meet your requirements, which is the same as picking out students who flipped 5 coins in a row. And so it's really important that before you do those analyses, and ideally at the very beginning, which is why medical journals require this, you've decided these are the variables we want to look at, this is why we think they're important, and now we start doing the study, and we will test it at the end. But in scientific papers, they don't always require, or they usually don't require that you do this. And so you can measure all your data and then try to find hypotheses in it afterwards.
So if you measure the data and then do a PCA to get the important features, that's not okay?
That's okay.
That's okay.
That's perfectly okay.
Yeah.
So you can do, so that's very commonly what they do. They do something like principal component analysis to bring down the number of features from 60 to 3. And then your threshold for finding a significant thing stays at sort of this 3 different variable threshold, not at the 60 variable threshold, but you incorporate a lot of this information together. You make your life then more difficult because you have to explain what it means to have a principal component that's significant, because it doesn't mean that all of its subcomponents are significant. You have to sort of decide what caused it. That when you have a PCA analysis, you moved away from real metrics like thickness or cell shape or size, and now you're at sort of a linear combination of features. And what that actually means in your sample isn't always clear.
So you would not be able to do it in a medical area?
You could, but you would have difficulty interpreting your results.
Like you said, you have to mention before starting the measurements, you have to say, I'm going to measure these things.
Yeah, but you have to say I'm measuring these things, and then you could say we then take all of these components, put them in a principal component analysis, and do the statistical assessment on the first 3 principal components. That's acceptable. If the review board would understand that is another question, but you have to sort of detail what tests you're doing beforehand. And typically with a setup like this, you wouldn't say principal component analysis unless you had actually seen some data before from some other study where that made sense. But typically, yeah, you can perform all of these analyses. It's just sort of you have to artificially blind yourself to the output while you're designing these hypotheses. Because if you can see this, then you can simply design hypotheses that make your results true. And that's not fair. And that's not a way of getting ultimately results that are predictive outside of the current experiment you did. And so that's really the important factor here. And these other 2 graphs just kind of show that further. And so you can then see the p-value for a 10% difference. And so this is where you have 2 random data sets that are 10% different. So you have a group of people that are, 10% taller, something like this. And this is the number of different samples you have in this study. And this is the p-value you get for a 10% difference. And so you see, if you have very few people, this p-value is still fairly high, and the more people you add, the lower this value drops. If you then take this and look at the number of different variables you have, this is your probability of finding a significant variable based on the number of variables you have and the number of samples. And so this is taking this sort of fixed 10% difference that we had before. And if you have one variable, then with 25 samples or so, you have over a 50% chance of actually showing this difference. But if you choose to look at 100 variables, then you have, a 15% chance of actually being able to show this difference that you want to show. Because you have these 100 extra variables hanging around, it makes the requirement for the difference that you actually observe much, much, much higher. And so if you want to be at the same point you were with 25 patients and one variable, you need to have, 75 or more if you have 100 variables. And so if you're dealing with a study where you have millions and millions of patients or millions and millions of data points, then you can do this. You can afford to look at more variables because you have sort of enough power in your data sets to show significant differences. But if you're dealing with very limited data sets, so a lot of biological studies will look at 12 animals or groups of 12 animals, then you're very limited on this end. And if you try to look at more than one or two variables, then you won't be able to see small differences at all. And so this really, it's just for one example type of study, but you can see clearly what effect increasing the number of variables has on your ability to find a significant result. And of course, if you have enough samples, all of these curves kind of converge together. That with enough sample data, you'll be able to show that there's a difference between these groups. It's just much harder with 100 than it would be with 1. Is that clear? Okay. Ooh. Okay, so I think we have quite a few slides left to cover. I'll try to cover a few more of them quickly, and then we can cover the rest at the beginning of next lecture. I think next lecture we have extra time. So the idea is that this sort of shifts gear completely away from what we had before, and this is looking at sort of a standard image processing work chain. And so that you have sort of your images come in here, you have sort of nodes that do this processing, and you have inputs to these nodes that sort of determine what kind of analysis you're doing. And so here you have the raw images go into your Gaussian filter. You have a 3x3 neighborhood and a sigma value of sort of 0.5. And then this Gaussian filter output goes to your threshold, and this gets the threshold value fed into it, and then this is fed out to the shape analysis, which then gives you information about all the shapes in your structures, and a thickness analysis, which gives you information about the thickness distribution in your structures. So this graph is really just to kind of see and have this directed acyclical graph view for how does an image analysis workflow kind of look. And this is where we have the data as well as the parameters shown as different nodes in the system. This will be particularly important for the future lectures where we talk about sort of machine learning and deep learning, because these are the structures that we use and the things that we try to optimize to perform those tasks. But here it's just sort of important to have the idea that there's sort of a flow here. Everything has to go sort of from input to output, and that you have things that are fixed, like the data that are coming in and the nodes that you're using. And then you have these gray things, which are parameters. So things that you decide, but you're not always very certain. And so what we see for sort of a, maybe a full chain, that if we look at kind of the exercises we did in each of the different lectures, you sort of started off with the raw images, and then you tried out different types of filters. So on the same input images, you tried a Gaussian filter, you tried a median filter, you tried a diffusion filter, you tried a Laplacian filter, whatever. So you have a list of different filters that you tried, and you looked at the output. And actually, in order to do this viably, at the next lecture, we then took some image and we looked at these 3 different types of segmentation on that image. But to do this viably, you really have to link all of these steps together. which means you have to take every image that you have, apply a Gaussian filter, median filter, diffusion filter, and then for each one of the images you have here, apply these different 3 types of thresholds, and then for each of these 3 different types of thresholds, apply all of your different analyses out to see which set of those parameters and which combination of these tools worked best. Because usually you don't really know a priori which ones of these are the best suited for the kind of analysis that you're doing. So you might suspect that diffusion and median will work best because your noise looks like the sort of noise that you've seen in examples before, or the process can be modeled very well by diffusion, but you don't always know. And so usually you have this sort of workflow that you're building out where the number of sort of options you have grow exponentially, and this isn't even showing the parameter space. So this is just showing the filters that you have and the thresholds. For each of these, you also have parameters that get fed into them that determine the analysis. And so yeah, to look at that one in more detail, you then sort of have what's the size of, you have different neighborhood sizes, you have different sigma sizes, and you have different sort of threshold values that feed into all of this. And so that basically this network gets many, many nodes very quickly, and it becomes a huge space that you sort of have to search through. And there's over 1,080 combinations for just one sample. And this isn't looking at a large range of thresholds, this is looking at a fairly narrow range of thresholds. And to calculate even one sample for this, I think if we take one of the 3D foam images we've looked at before, would take 12 weeks of processing time to evaluate all of these different options. To do this for the femur samples, where it's 1,000 by 1,000 by 1,000, it would then take 2 years to do it for all of them. This then isn't very helpful because it's only one sample, and actually you'd want to run it on all the samples because not all the samples are the same. And so how do you really judge the different results? So how can you take this output and start to do something meaningful with it? And so we saw for the imaging, you have this idea of this ROC curve that you can try to improve to get sort of those imaging components to work well. But for this, we have a lot of other outputs that are coming out that don't necessarily fit well into this ROC model. So you have things coming out like shape or anisotropy or volumes or distributions, and you can't really do a true positive, false positive assessment on this because you just get a number out. And so this is where we kind of look at what are the differences between qualitative and quantitative assessment. And this qualitative is kind of looking at the images and seeing are there artifacts, are there problems, are there things that get better, things that get worse. This is what we try to cover as much as possible with that ROC curve. And so here you can kind of look at 3 different samples with 3 different types of filters and determine did it do a good job at seeing the structures in the sample that you were trying to see. And then the quantitative metrics are sort of looking at all of the output values we have and trying to assess something meaningful about them. So of course, in the ideal situation, you know what the output value should be. So you know the number of cells, or you know the shape the cells should have, or you know the thickness of the vessels that you're looking at. But a lot of times you don't have that. And so one of the things you can do is you can sort of do this parameter sweep where you change the parameters you're feeding into your system and you look at how the output changes. And so this is called sort of a sensitivity analysis. So you can take, for example, different threshold values on your system and look at the average volume at the output. So here you see sort of the volume distribution change, and you see the curve sort of fluctuate a little bit. But if you were looking at this curve, the 250 average volume that you get out isn't affected that much by the range of thresholds that are reasonable. So between this 2,000 and 8,000, that curve is fairly flat. There's slight variations, but it's not too substantial. Or here you see the whole distribution a little better displayed, and that distribution doesn't change too much. As the threshold gets really high, you see that it starts to sort of compress towards the smaller volumes, but ultimately the differences aren't that big, which means that you're not very sensitive to this threshold value. If you look at another metric like orientation, so this goes between kind of -1 and 1, you can see that the mean value of this changes much more as you change this threshold. And so basically what we want to define here is this idea of the sensitivity. So how much does a change, a small delta change in your parameter, have a change in the output that you're getting at the end? And so this is sort of from material science or these other things. The units don't always make sense. And so if you're looking at a metric that's volume and your parameter's threshold, then you're looking at sort of meters cubed per intensity unit, which probably doesn't mean very much. But the idea is to look at sort of the shape that this curve has. And so, yeah, you can sort of also make it more practical by looking at sort of the max over the min divided by the average. So that gives you an idea of some variability that you're seeing inside of this metric rather than looking at just the metric itself. And that what we see here is sort of the example of what kind of curves you can get out of this. And so looking at this curve, if this is your object count versus your threshold, where would you perform the threshold? So assuming that all of the images are fairly similar looking at the end, and you want to use this curve so that the threshold you have is the most reliable one, and small variations in your image are unlikely to cause lots of changes, where would you take it? Where?
Around 5,000.
Yeah. Why?
We'll have fewer objects, so noise would be unlikely to affect them. Because if we have more objects, then it's more likely that noise can affect what we see.
Yeah.
I would go with 5,500 because then a small variation in a threshold would make only a small variation count.
Right.
To where the slope of the is farthest closest to the count.
Right. So that's what
you'd be less sensitive. So you.
Yeah. So when you go here, this whole region, you see that the slope here is very low. So the change in your metric compared to the change in your threshold is very small. And if you look at this region, like here, this is a very steep slope, which means by changing your threshold a little bit, you change your output value a lot. And so actually having a low object count is usually bad because that means if you have one extra object, you change your whole result a lot. If you have 20 cells in your image and you accidentally find one cell too many, then you have 21, which is then, 5%. If you have 100,000 cells in your image and you accidentally find one more, it doesn't really affect your result very much. Or if one of the things you find isn't actually a cell, it's an artifact, it's not really a big problem. So with things like object count, you'd actually like it to be as high as possible, but you want this curve to be very flat. And so by looking at these curves, even if you don't necessarily know what the value is supposed to be, you can see that in this region, it's very stable. And so that's the region you can make your measurements in. And so you can make these curves for sort of all of the different parameters in your system or the metrics that are important for you so that you can be confident if there are variations in your image or if there are slight fluctuations, it's not changing your output completely. Yeah.
So this is just deciding which threshold range to use to establish stability in what you're getting as a result, but it doesn't say anything about the truth of the result.
Right.
There is a truth.
But usually what you can do is you can have kind of this 2,000 to 8,000 are the thresholds that make sense. So that you might know from your sample if you're looking at, blood inside of a human body, that the absorption has to be somewhere between 2,000 and 8,000 in these units so that you can be confident that you're actually seeing blood. If it's 15,000, this curve might be perfectly flat, but then you're looking at bone or then you're looking at fat. And so you usually have some boundaries that are kind of dictated by your data, by what you sort of expect to see, but you can't really decide which of these thresholds looks best. So that when you're trying to play around with the value, you don't see. Ideally, you have ground truth where you can say, this is the perfect answer we need. And so we simply adjust the parameters so that we get the perfect answer. But in data sets where you don't have this, then you have to kind of look at these proxies of, okay, this threshold value is very stable, which means if we're doing lots of analyses on different samples, the variation that's being added by small changes in threshold or small changes in the average intensity are very minimal compared to the sort of overall output, or as low as they can possibly be. And so that's really the idea with making these kind of curves. And so if you look at 3 different metrics here for these cells, that you can take sort of count, volume, and anisotropy, and they have usually very different shapes, but ideally you can find a point where they're as flat as possible for all of them. And so here you have these 3 different parameters, and you kind of find, okay, between 5,000 and 6,000, it works for all of them. Or because volume is the most important metric for me, I optimize that curve, but I see that these other metrics are also valid. But one of the things that this graph makes fairly clear is how reliable is your metric going to be in the face of sort of small fluctuations. So this will give you kind of an indicator before you've done all your analysis at something like ICC. So if this curve is really, really steep, the chance that your ICC value is high when you're comparing 2 groups is going to be very, very low. Because there's going to be a lot of variation between the groups, because this curve is so steep that small fluctuations will cause large differences, and you won't actually be able to see the differences between the samples. So a steep curve here means that you'll have a high S variation in this W. So within a single group, you would expect that variation will probably be much higher because this curve is much steeper. If this curve is completely flat, then you'd expect that to be fairly low. Okay, so I think we'll stop there, and we'll have the other slides at the beginning of next lecture. Otherwise, we'll go way too long. So are there any questions on that, on those topics that we've covered? Okay, so the exercises have been updated since I put them on first last night. I think the first ones that went on there weren't quite correct.